Yeah. So in the last class we have started discussing about orthonormal expansion, no vector space. So signal space concepts. So we have started about discussing signal space concepts, and today we will continue with that and we'll complete this topic. Yeah. So as a part of this, we kind of recalled the vector space concepts in the last class. Vector space concepts like norm of a vector and what are mainly the basis vectors. What is an n-dimensional vector? What are the basis vectors? When do we call two vectors as orthogonal? The set of linearly independent vectors. And then we wanted to define the similar things for signals as well. In the sense we have defined inner product of vectors, and similarly we have defined inner product for signals. And then norm of a vector, and then norm of a signal, and then orthogonality in terms of signals, right? So define inner product, norm, inner product and norm of for signals. And then we define when do we call two signals as orthogonal signals. We define orthogonal signals, etc. So while doing so, when I looked at the notes, when I went back and looked at the notes, I found one mistake that I did. So see, for example, here, when we define the norm, yeah. So in the previous class, when we defined the norm of a signal, norm is, it should be norm of x of t, should be, we have defined that as an inner product, but it should be square root of inner product. So it should be power half. So in that sense, it should be power half, right? And similarly, it should be power half. In that case, it is square root of energy, right? So please make this correction. So norm of a signal is square root of the inner product of the signal with itself. Like inner product of x of t with x of t under root. So it should be square root of energy of, right? So maybe I'll write this. So here, once this change happens, then here also we should correspondingly change this. Yep. So correcting the error. Norm of a signal x of t is nothing but x of t that is equal to x of t with x of t conjugate dt, and this is power of. So this is minus infinity to plus infinity. Yep. So this we can directly write this as square root of energy of x of t. So that is equal to square root of dx. So this was a mistake done in the last class. So please correct all of you. So so norm of a signal is this. So then we'll start with today's class, right? Right. Say if you okay. So now we will develop signal space concepts, and especially in this class we will do orthonormal expansion of signals. We will do orthonormal expansion of signals. Yes. So why do we do this? See, if you recall, what we thought was an n-dimensional vector can be represented in terms of basis vectors, right? So so simply an n-dimensional vector has got n components. Say if V is an n-dimensional vector, then it has got V1, V2, and so on up to Vn transpose. So we want to represent signals as vectors. So recall our motivation for this topic is we wanted to represent signals as vectors. So if I am given a signal S of t, then I should be able to represent this S of t as as a vector S1 having n components, S1 up to Sn, with respect to some basis vectors, or with respect to some signals that span this. So we'll be doing that. So yeah. So let's start with this. Consider finite energy signals. So we will be considering for this task only the finite energy continuous time signal. Continuous time signals. Right? And just consider one signal. Let S of t be one such signal. So what does it mean? So S of t has got finite energy, right? So when I say S of t be one such signal, that means S of t has got finite energy and it's a continuous time signal. So that meaning norm square of S of t, which is equal to energy of S, energy of S of t is a finite quantity. It's not infinite, right? It's a finite quantity. So let S of t be one such signal, and let phi n of t n equal to 1 to up to k be a set of orthonormal signals. Right? So we have a set of signals, phi 1 of t, phi 2 of t, and so on up to phi capital K of t, which are all mutually orthogonal. So, and each signal has a unit norm. So these orthonormal signals these signals are mutually orthogonal to each other, and they all have unit norm. That meaning, what do that mean? So phi n of t. So inner product of any of these two signals, which is nothing but minus infinity to plus infinity, phi n of t is equal to 1 if n equal to m, right? So this is equal to 1 if n equal to m, and this is 0 if n not equal to m. So that is the meaning of these signals.
Hello.
Hello.
Tell me, sir.
No. I'm continuing my class. So these are set of orthonormal signals. Now we will try to express this signal S of t. So now we have S of t and a set of orthonormal signals. Then our intention is to express, let's try to express S of t as a weighted linear combination of these signals phi n of t, where n equal to 1 to capital K. Right? So what we are trying to do is we want to represent this S of t as a linear combination Sk pi k of t, k equal to 1 to capital K. See, please note that this is a small k, lowercase k, this is uppercase k. This is a capital K, this is small k, right? So we want now in almost the entire class, what we will try to do is, when can we represent this signal S of t, which is a finite energy signal, as a linear combination of a set of orthonormal signals pi k of t, k equal to 1 to capital K, right? So as I'm saying, this is only an approximation of signal. So let's call this as S hat of t, right? So S hat of t is an approximation of S of t. And what we'll ask questions and then solve these things as when is S hat of t is good enough. Right? So we are trying to represent S of t as a weighted linear combination of a set of orthonormal signals, and that meaning, so this is simply equal to some S1 into phi 1 of t plus S2 into phi 2 of t, and so on up to S capital K into phi k of t. So we have k signals, and then we want to find a linear combination of these signals such that a linear combination of these signals is equivalent to S of t. So till now it is not exactly equivalent to S of t. So that's why I represented this as S hat of t. So as there is a hat on top of S, we call this signal as S hat. We call this signal as S hat of t. Right? So now we are not sure whether S hat of t is equivalent to S of t or not, right? So that's why let's define an error signal. So error signal E of t is equal to S of t minus S hat of t. Right? So this makes sense, right? So we are trying to represent S of t as a linear combination of these terms, and that we are calling it as S hat of t, but it is not exactly equivalent to S of t. So that's why we are trying to construct an error signal, which is E of t is equal to S of t minus S hat of t. Okay. Now, when do we say that we have done a, when do we say that S hat of t is equivalent to S of t? We'll also define energy of error signal. We define that as E subscript E, that is equal to S of t modulus of S of t minus S hat of t whole square dt minus infinity to plus infinity. Right? Okay. So now if we want to have S of t as close to S, if we want to have S hat of t as close to S of t as possible, then what do we want? We want energy in the error signal to be minimum. We want to minimize energy in the error signal. In other words, we want to find the, I'll write this in the next page. So what I'm trying to say is we want to find these coefficients S1, S2, S3, S4 up to Sk in such a way that the energy in the error signal is minimum. So we are given S of t, a finite energy signal, and we are given a set of orthonormal functions, phi 1 of t, phi 2 of t up to phi k of t, right? So, and now we want to express S of t in terms of as a linear combination of these orthonormal signals, and these S1, S2 up to Sk are the coefficients of the linear combination. So we are multiplying first orthonormal signal with the coefficient S1, we are multiplying the second orthonormal signal with the coefficient S2, and so on, and then we are adding them up to get S of t. But we are not, we don't simply get S of t by doing this. We have to find these coefficients in such a way that there should be some criteria to find these coefficients. so that this expansion is equivalent to the S of t. So what I'm trying to say is that we want to find these quotients such a way that energy in the error signal, what is the error signal? The original S of t minus representation of S of t as a linear combination of orthonormal functions, right? So that's what we want to do. So we want to determine the quotients Sk, k equal to 1 to capital K, such that they minimize energy in the error signal. So this is okay. So till this point, I hope this is clear. We just set up the problem and then we want to solve this out. So there are two methods to find these quotients Sk that minimize the error signal. So one method is to differentiate this expression. One method is, all of you know this kind of method. Differentiate the energy in the error signal with respect to each of the quotients. Sk, k equal to 1 to capital K, and set the first derivative to 0. Right? So let's recall what is EE. EE is S of t minus S hat of t whole square dt, right? So this is again nothing but S of t minus S hat of t is what? It's a linear combination, right? K is equal to 1 to capital K, Sk, phi k of t whole square dt. So what we are trying to say that you differentiate this expression. You first differentiate this with respect to S1 and set the first derivative to 0 and find S1. And then like you will be having K equations when you differentiate this with respect to each of the quotients and then find the optimal quotients. So this is a very laborious process, right? So this is a very lengthy process. So we won't use this approach. So what I'm trying to say is this is one of the standard approaches. Like you can even if you forget all other approaches, you can do this because you just if a function when E is a function of all these SKs, and we want to find out these SKs such that EE is minimum, you have to differentiate this EE with respect to these parameters and then set the first derivative to be 0. Right? So it is a, so let me also call that, let me also say that so it is a lengthy process. Now, an alternative method to this is the following. We use a standard result from estimation theory. So when you study your masters or when you go for MS, so you will there will be a specialized subject called estimation theory. So in you need not understand, you need not go through estimation theory right now for this purpose, but there is a standard result, very basic result from estimation theory, which we will state now, and then we will use that result to find out our orthonormal expansion, to find out our S1 to Sk. We use a standard result from so let me just correct this. We use the following standard result from estimation theory, right? That is minimum of E with respect to the quotients Sk is obtained when E of t is orthogonal to when the error signal, so E of t is the error signal, right? When E of t is orthogonal to each phi n of t n is equal to 1 to capital K. Yes. See, this result, I'm saying we need not worry about how exactly this result has come. We need not derive this result, but we will make use of this result. Right? So what does this mean is, so this implies that E will be minimum. E is energy in the error signal. E will be minimum when, so whatever we said in words in the above, we are trying to write in maths in the below, when E of t is orthogonal to each of the orthonormal functions. Dt equal to 0 for n is equal to 1, 2, up to capital K. So let's expand this a bit. So this minus infinity to plus infinity. E of t is what? S of t minus K equal to capital K, Sk, phi k of t into phi n star of t dt equal to 0, where n equal to 1 to capital K. Right? So this equation is nothing but this equation. So now we have k such equations, right? So using these equations, like this integral of this is equal to 0. Using such equations, we want to find out the quotients Sk, right? So now let's take one of these equations. So we have n such equations, right? So integral s of t minus this multiplied by phi 1 star of t dt equal to 0, and so on and so forth. So we have capital K equations to find out S1, S2 up to S capital K. Okay. So now let's find out what these quotients should be. So consider one of these equations by fixing n to a particular value between 1 and k, right? So that equation will be minus infinity to plus infinity s of t minus small k equal to 1 to capital K Sk phi k of t into phi n star of t dt equal to 0. So this is nothing but minus infinity to plus infinity s of t phi n star of t dt equal to, so these are two integrals, right? This multiplied by this and this term multiplied by this. So I'm just writing them to be separate into k equal to 1 to capital K Sk phi k of t into phi n conjugate of t dt, right? So this equation I just rewrote in this form. I sent this integral to the right hand side of the equality and I got this. Now let's focus on this integral. Okay. Let's interchange the summation and the integral. Let's interchange the integral So when I say integral, this is this integration sign, right? Integral and the summation. So that meaning this happens what? This k equal to 1 to capital K minus infinity to plus infinity sk phi k of t phi n star of t dt. Right? So here, let me tell you something important, that can we always interchange these two signs? Okay, so I'm not going into that details because we don't have much time, but you should be knowing from your math courses that we cannot always interchange integral with summation. We cannot always move these two things like this. See, here first comes the integral, then the summation. Here we just interchange it. That we first got the summation and then the integral, right? So this we can do only under a few circumstances when these signals obey the Fubini's theorem, right? So this you must be learning from your math courses. If you haven't learned in your undergraduate, you will definitely learn in your masters when you go for masters. But only thing I want to caution you that in almost in all UG courses you can do this, because the signals you encounter will be such that you can do this interchange. But in general you cannot take it for granted. So this depends on something called Fubini's theorem. So those who are interested in math, those who are I know that some of you will be very much interested in going deep into mathematics. So they can look at these theorem in Wikipedia, or you can find it in some of the standard textbooks, maths textbooks. So right now don't worry about this. Okay. So now we interchange these two things. And then what will be this? So this integral, see, this k will be varying from 1 to k. So this will be S1 phi 1 of t multiplied by phi n conjugate of t dt, S2 phi 2 of t multiplied by phi n conjugate of t dt. So this integral, this becomes 1 only when k becomes n. And is 0 when k not equal to n. Do you agree? Because see, the signals are orthonormal. Okay, let me. So whatever I have written is correct. I'm not erasing them because they are wrong, but I want to add something more here. So now recall that phi n of t, n is equal to 1 to capital K, or orthonormal signals. Hence, this becomes 1 when n equal to k, and 0 when n not equal to k. Or it can be the other way. It can be when k equal to n, right? So that meaning minus infinity to plus infinity s of t phi n star of t is equal to Sn. So when this summation becomes, when this k becomes n, then only we will have this here. Okay, yeah. So this is it. Thus, the quotients that minimize E are given by Sn is equal to minus infinity to plus infinity S of t phi n star of t dt, for n is equal to 1, 2 up to capital K. Okay, so these are the optimal coefficients. So these are the optimal coefficients that minimize So why do we say they are optimal? They are optimal in what sense? They are optimal because they minimize the error energy. Fine. Okay. Now we found out what are the values of these coefficients that minimize the error energy. But with these optimal values of Sn, what will be that minimum error energy? Right. So what is that minimum error energy? So let's not call this, not a proper word. Minimum energy of the error signal So we are saying the energy in the error signal will get minimized, but will it go to zero? What is that minimum? Is it 1? Is it 2? Or is it go to, does it always goes to 0, or what is that? So let's find out that. So what is that minimum energy of the error signal achieved by these optimal coefficients? So that we try to call it as EE minimum, EE min, right? So EE min is nothing but, so let's see this. Okay, so before going to this, yeah. So we'll answer this question in just 1 minute. So before that, so let's pause for a moment and then see what we did. So let's try to find out one coefficients are obtained. Okay, this is nothing but, so I want to give one interpretation, physical interpretation of what is this SN. So this is nothing but projection of S of t onto phi n of t gives us optimal quotient Sn. So in math, we'll simply write integral minus infinity to plus infinity s of t multiplied by phi n conjugate of t dt. But what does it means? That there is a signal s of t. We are projecting that signal onto the nth orthonormal function phi n of t, right? Or in other words, this is nothing but inner product of s of t and phi n of t. Do you agree? See, this is nothing but inner product of s of t and phi n of t, right? So I'm writing that here. That implies Sn is s of t phi n of t, inner product of these two, right? So just keep that in the back of your mind, that the optimal coefficients are obtained by taking the inner product of s of t with the orthonormal functions. So if you want to find the coefficient S10, you have to take inner product of s of t with phi 10 of t, that the 10th orthonormal function. Okay. So now with that let's get back to this question. Let's get back to this question. What is the minimum energy of the error signal that is achieved by the optimal functions? So let's to solve this, let's again go to the basic equation. E of t is s of t minus s hat of t, right? From this only we came up to all these things. So this implies s of t is equal to E of t plus s hat of t that is equal to E of t plus s hat of t is what? Summation small k is equal to 1 to capital K and then sk phi k of t. So this is this, right? So now we want to find a similar equation which relates these energies. So when the signal s of t is nothing but the error signal E of t, the error signal E of t plus s hat of t in energy terms. So this happens, what happens is error in the signal s of t is equal to error in the energy signal plus error in the s hat of t. Right? Or okay, so in other words, so integral minus infinity to plus infinity. Okay, so let me, this may be a little bit confusing. So where are we? We are here. Okay, so fine. So then this equal to minus infinity to plus infinity E of t k equal to 1 to capital K sk phi k of t whole square dt, right? So this right hand side equation, so this is nothing but minus infinity to plus infinity E of t plus summation sk phi k of t, k equal to 1 to capital K. This multiplied by its E of t, k equal to 1 to capital K, sk phi k of t conjugate dt. See, this is nothing but a complex signal, possibly a complex signal, right? So I want to write mod of a plus jb whole square. So this is nothing but a plus jb multiplied by a minus jb. Right? So that is what I am writing here. So this is nothing but e of t plus this multiplied by its conjugate. Now we will have e of t multiplied by e conjugate of t, this signal multiplied by this signal conjugate of t, and then there is a cross term. So here what we will be having is minus infinity to plus infinity e of t whole square dt. So that is this signal, this first signal multiplied by this signal, right? And then this multiplied by this will be the second signal plus integral minus infinity to plus infinity. How should we write this? I equal to 1 to capital K, j equal to 1 to capital K, si sj conjugate phi I of t, phi j conjugate of t dt. See, when this summation multiplied by this summation I have to write, I cannot write the same k two times. Small k is equal to 1 to capital K here, and also small k equal to 1 to capital K here. So I cannot do these two things simultaneously. So I introduce another dummy variable. So here the dummy variable is si, I is the dummy variable. Here the dummy variable is j. Fine. So now we have got these two terms plus what will be the other two terms? This e of t multiplied by this plus this conjugate multiplied by plus, so minus infinity to plus infinity e of t multiplied by k equal to 1 to capital K, sk conjugate phi k conjugate of t dt plus again minus infinity to plus infinity k equal to 1 to capital K, sk phi k of t multiplied by e conjugate of t dt. Now so what I claim is this integral will become 0. This will be 0 and this will be 0. Why? So think about this for a minute. Why am I saying that this integral e of t multiplied by this term goes to 0 and this multiplied by e conjugate of t goes to 0? Because we found these coefficients sk's by using the principle that, see, how did we find these SKs? We found that assuming that the error signal is orthogonal to all the orthonormal functions, right? So we found that when E of t is orthogonal to phi n of t, when E of t is orthogonal to phi 1 of t, when E of t is orthogonal to phi 2 of t, when E of t is orthogonal to phi k of t, when E of t is orthogonal to all phi 1 to phi k of t's, then we found these quotients. Now we are using those quotients and solving some equations. So that meaning this E of t should be orthogonal to phi k star phi k of t, right? So that's why this integral should be 0. Similarly, E star of t multiplied by phi k of t should be 0, right? Remember that we have obtained optimal values of Sk, k equal to 1 to capital K, assuming that E of t is orthogonal to phi n of t. Hence, the last two integrals on the right hand side becomes 0. So that implies S of t dt is equal to minus infinity to plus infinity dt plus what we should have it here. So let's turn the page back and then let's see that. Okay, so we said this integral is going to be 0, this integral is going to be 0, and we are left with these two integrals. So the first integral is nothing but energy in the error signal, and the second integral, so let's solve this out. So this, in the second integral also you apply the orthonormal property of these functions phi's. So when phi I of t multiplied by phi j conjugate of t dt will be 0 when I is not equal to j, right? So in this integral, when I is not equal to j, this term will become 0 because phi I is orthogonal to phi j, and when I equal to j, it becomes phi I of t multiplied by phi I conjugate of t dt, right? So in that case, this becomes 1. So when this becomes 1, this will be Si multiplied by Si conjugate. Si multiplied by Si conjugate will be mod Si square. So if you do a little bit of algebra here, what you get here is, so this plus k equal to 1 to capital K, so this is what we get. right? So finally, and what do we call this? This is energy in the error signal when we use optimal coefficients. So let's call that as E minimum, right? So E minimum is equivalent to minus infinity to plus infinity mod s of t square dt minus k equal to 1 to capital K sk square, right? So I'm trying to write that as, right? Okay. So what is this? Now what is this integral? I'm claiming this integral to be energy in the s hat, and this integral we know this is energy in the signal s. This energy in the signal, this integral is nothing but energy in the signal s of t, and I'm claiming the summation of mod sk squares where k varies from 1 to capital K is energy in the es hat and energy in the s hat of t. So is that correct? Yes, this energy, if you try to find, we know s hat of t, right? So as a small homework, s hat of t is k equal to 1 to capital K sk pi k of t, find its energy. In fact, we did this exactly in the previous phase, but I just wanted to see whether you got that point or not. Okay, so you just solve this, find its energy. It should be equal to 1 to capital K mod sk square. Okay, yeah. Now when E minimum is equal to 0, energy in the original signal s hat s of t is equivalent to energy in the approximate signal s hat of t. That implies is equal to right. So when this thing happens, when the energy in the error signal becomes 0, then we say that these orthonormal functions are a complete set to represent any finite energy signal, right? So okay, so let Now, just to conclude this topic, like of course we need to discuss some more at one more point, but consider a clause. Okay, so just keep this aside. Keep this aside for a moment, and then focus on the next point. Consider a class of signals. Okay, let me not write as soft. You will get confused again. Consider a class of signals calligraphic C. So consider a class of signals C. Okay, then a set of orthonormal functions, are said to be complete for the class of signals C if the error energy approaches energy is 0 for all the signals that belong to the class C. Yeah, so I request you to first note down this statement, then we will discuss about this statement. Right? So let's pause here for a moment. You please make a note of this statement, then we'll discuss what does it mean in detail. Right? Okay, so hope all of you have noted this. So what does this mean? This means that say consider a class of signals. So let me give you an example for this definition. So we have written a long statement. Consider a class of signals denoted by C, and that is a calligraphic C, and a set of orthonormal functions are said to be complete, or the set of orthonormal functions said to span the class C if the error energy is 0 for all the signals that belong to class C. Okay, so the better way to explain this is to consider an example. So let's consider an example. So consider the class of signals. Consider the class of signals that are square integrable and 0 outside minus t by 2 to plus t by 2. That means here my class of signals is set of all signals that are square integrable and 0 outside the interval minus t by 2 to plus t by 2. So this is what we mean by the class of signals, right? So square integrable, what do we mean by square integrable? Square integrable is nothing but they are finite energy signals, because if a signal is s of t, if I say that the signal is square integrable, that meaning mod this becomes this is finite, right? So consider all finite energy signals that are defined only in the interval minus t by 2 to plus t by 2 to be non-zero, and they are 0 outside this interval. Then then the set of orthonormal functions phi n of t is equal to 1 by square root of t e to the power j 2 pi nt by capital T for minus t by 2, t by 2 and 0 elsewhere. Is a complete set of orthonormal functions to represent signals in C. So if C is a set of all signals that are square integrable and they are 0 outside the interval minus t by 2 to plus t by 2, then the set of orthonormal functions defined by this equation, these orthonormal functions are complete for the signals in C. So these orthonormal functions are complete to represent the signals in C. What do we mean by that? You take any signal in this class. You take any signal. This set C may contain S1 of t, S2 of t, S3 of t, some X of t, Y of t, Z of t, whatever. So all those signals are square integrable and they are 0 outside this interval. So you take any such signal and then you can express that signal as a linear combination of these orthonormal functions. So if you take any signal from this set C, then you can represent that signal as a weighted linear combination of these orthonormal functions, such that the error energy becomes 0. So we call that's why this set of orthonormal functions is a complete set. So this set of orthonormal functions is a complete set for any signal that belong to class C. And this is nothing but your exponential Fourier series. So our next topic is Fourier series representation of signals, and this is where from this Fourier series comes. Fourier series comes from the orthonormal expansion of signals, right? So this example, of course, we are not defining Fourier series from this. So we'll separately from next class onwards, we will deal separately with Fourier series because that's one of the most important concepts in signals and systems. So, but this example is these signals are nothing but these exponential Fourier series signals, right? So just remember this word exponential Fourier series. I'm putting that in brackets because you will we will discuss this exponential Fourier series separately, and then you will realize that, oh, okay, whatever we are discussing now, this is what we have seen in terms of orthonormal expansions, right? So that's one thing. And then one more, okay. So we have seen this entire derivation in the sense we have taken a finite energy signal S of t, and then we try to express that as a linear combination of orthonormal functions. So we have a set of orthonormal functions, and we try to express S of t as a linear combination of orthonormal functions. Then we wanted to find these coefficients in such a way that energy in the error signal is minimum. So this that this term, yeah, sorry. So I forgot to say one thing. We focused on minimizing minus infinity to plus infinity S hat of t right. In the entire class today we focused on minimizing this. So, and this we defined error signal as S of t minus S hat of t, and then we focused on minimizing this. So this is called mean square error. See, this is the error, right? So this is the error signal, and S of t minus S hat of t square is the squared error, the error square, right? And we try to find energy in this signal. So this is one thing. So note that uh, huh, uh, note that S hat of t okay, so okay, so I'm just trying to find a proper word. S hat of t converges to S of t uh, in the sense that s of t minus s hat of t dt goes to 0. So so maybe I'm trying, I'm not putting it correctly. Okay, now I can say it more effectively. So what I'm trying to say is, see, we have a signal s of t, and we are trying to build a signal s hat of t, right, using set of orthonormal functions or whatever. Then s hat of t is equivalent to s of t in what sense? In the sense that the energy in the error signal is minimum. We are not saying that the error signal is minimum. We are only saying that the energy in the error signal is minimum. Meaning, we are not trying to make s of t minus s hat of t goes to 0. We are trying to make s of t minus s hat of t whole square goes to 0 on the average. We are not doing this. We are not trying to do this, or we haven't tried to do this. We did this, right? So we haven't tried to do that s of t should be equivalent to s hat of t at every point. All that we tried to do was, we wanted to see that s of t may not be exactly equivalent to s hat of t, but the energy in the error signal goes to 0 with the obtained quotients and the orthonormal functions, right? So that meaning this you should keep it in mind. So whenever you represent s of t in using orthonormal expansions, you get a signal s hat of t. So this s of t and s hat of t need not be exactly the same at every point. But the error energy s of t minus s hat of t, that mod square integral over minus infinity to plus infinity, should be 0, right? So you are trying to construct s hat of t in such a way that the energy in the error signal, where error signal is given by s of t minus s hat of t, goes to 0, but not that error signal goes to 0. So we are not focusing on making error signal going to 0. We are focusing on making the energy in the error signal going to 0. So this point you should keep it in your mind. In other words, we are not worried about making e of t to be 0. We are focusing on making energy of e of t to be 0. Yeah, this is one of the very important observations that you should keep it in mind. When you study sampling theorem, and then when you study estimation theory in future, you will get this concept again and again, right? Yeah. So we'll be having an extra class on Saturday morning. Saturday afternoon, and then we will start this Fourier series in that. And then yeah, and then we should take one more extra class. Like I missed 3 classes. Like so I covered one class, but I have to cover 2 more classes, and then hopefully we can definitely complete this 4-year series within next 2 weeks. Yeah. So with that I'm trying to stop my class today here.